I said that there is an easy way to do the common tangent, and there is, and it is basically by cheating, right? We observe that the points are already sorted because they're on the convex hull or they're on the upper hull, so we can just use gram scan. Based on the previous analysis of the gram scan, I can just compute the convex hull of the union of P and Q in linear time because the points are already sorted. Okay, so that's easy. So you can just merge them in linear time after find the common tangent. So therefore, the merging step is linear time, finding the median is linear time algorithm, recursion, every subproblem has a size n over 2. So if you write the recursion for this, you have f of n, which is the running time of the divide and conquer, equals 2 times f of n half plus O of n, and by Master's theorem, that's n log n. All right, so that's an easy way of finding that it's n log n time. But that's kind of cheating. Okay, that's not super exciting. And the thing is, for this algorithm does not make any difference. So even if you could merge faster than linear time, it's still that step of the algorithm takes O of n time. And obviously you cannot improve beyond n log n, as we're going to see later on. So really there is no hope to improve this algorithm. But maybe you could be not happy with this solution. Maybe you could say that I can do better when it comes to just the problem of finding common tangents. And it is actually true. You can do better. So let's see if we can do better than linear time for finding common tangents. Let's look at a simpler problem. So forget about this other upper hull. Imagine that the other upper hull is just a single point. So I have a point QI, and I have an upper hull P, and I want to find the tangent from this point to this upper hull. So in this picture, it looks like this. And I want to do it in log n time using some kind of a binary search. How do I do this? Okay, so binary search, what does binary search mean? It means that I start somewhere in the middle of this polygon. Let's say this point is the point with in the middle of the polygon in terms of its rank. Then when I look at this point, a binary search would tell me which way I need to go, right? So the common tangency is over there. So somehow I should figure out I need to go that way. But if I look at that point, then somehow I need to figure out that I need to go that way. Now the question is, and you can try to pause the video for this, what kind of observation you can make about these pictures that tell you which way to go. If this picture is a bit misleading, let me make it a bit more clear. So let's say I have this upper hull, and then you have a point Q that is outside this upper hull. Let's say I'm looking at point, this is the middle point, right? So the upper hull is made by point P1 up to Pn. To do binary search, you look at the middle guy. So let's say this is point Pn half. And I want to know whether I need to go that way or the other way. If I could know which way to go, then I could repeat this and I would find the tangent in log n time, right? Because there are n half vertices here, n half points here. If I know which way to go, I'm done. Now the question is, how do I do this? Try to pause the video and then see if you can solve this. Okay, so I hope you have thought about this for a bit, but the answer is actually very nice. Let me go back to my picture here. I actually kind of had a hint for you guys. So I want to know when I'm looking at point Pj and a point Q or Qi, I want to know whether the common tangency is that way or that way. The trick is to look at the neighbors of Pj. So I'm looking at the vertices before and after Pj on the upper hull P. Okay. In this case, I can see that the point Pi minus 1 is below, whereas point Pj plus 1 is above, right? So this is above. This would tell me that the common tangent is in that direction. Because it would tell me that the line segment that connects Pj to Qi goes through the convex hull. Because the upper hull is making a right turn. Okay. But now let's look at the other case. Look at this case. In this case, the point that was before pj minus 1, this is above the line, this line, and the next point is below. So the previous point was above, the next point was below. Wait, sorry, I should not have erased this. So this is above, this is below. When you compare it with this other picture, this was below and this one above. There's a little bit of difference. They are exactly the opposite. The point after is above. Here the point after is below. Here the point before is below. Here the point before is above. Right? By comparing which case I have, I can easily know which way I need to go. How do I know when I found the common tangent? Well, that's also easy. When you're at the position pj, such that both pj minus 1 and pj plus 1 are below the line segment, or the line that goes through pj and qi, then you have found the common tangent, because that's actually the definition of tangency, right? The polygon completely lies below the line, and that requires that both neighbors of pj lie below the line. Okay, so it's actually a very simple binary search, using any sort of implementation of binary search, and we have a termination condition as well. Okay, so that's how we can find the common tangent from one point to a polygon. And this obviously takes log n time, because every one of these is essentially a siderness test, which can be done in constant time, and I need to do this only log n time, because every time I resolve a test, I have the number of vertices that I need to consider.